Let me introduce to the open source tools PrePoMax and Calculix. We are going to use these two tools for all our hands-on exercises and through workshops throughout the course. Calculix is open source FEA solver. It has its own pre-processing and post-processing capabilities. However, we will be using PrePoMax as a preprocessor because this is very user-friendly GUI. And also the FEA workflow or defining FEA inputs is very similar to Abacus in PrePoMax. In fact, the input file format of Calculix solver, that is the input keywords, are mostly 90 to 95 percentage same as Abacus. So if you learn one software, other softwares are very quick to pick up because most of the softwares, FEA softwares, have similar workflows. But note that the solver capabilities of Calculix is not that advanced uh, that most FEA commercial FEA softwares offer. However, for learning concepts and for learning practical applications of FEA, these tools are great. Once you understand the gap between theory and practical application, you can use any tool with more confidence and you can perform FEA projects in or in timely manner. You can finish FEA projects with the confidence. So with this, let's have a look at a PrePoMax. You can download from this link. Let me show you the download page here. Okay, you can download the latest version from here, and the installation is very easy. In fact, you don't need to install PrePoMax. It is a portable uh, version. Okay, that means you can directly double click executable file and open the PrePoMax. And solver Calculix is will work in the background of PrePoMax. That means solver is already supplied with the PrePoMax package. Okay, let's take a simple example and try to understand the user interface of PrePoMax and also uh, FEA workflow. We will take this simple plate with hole example. The dimensions are given. The diameter of hole is 10 mm and the width of plate is 40 mm. So we will study the stress concentration near the hole under the external force of 4000 Newton. So this is a problem definition, uh, but we will take the quarter symmetric model because all the loads and boundary conditions are symmetric. So this is our FEA domain, okay, which is a quarter symmetric domain of original geometry. This edge of plate, okay, we need to assign symmetric boundary conditions. Okay, so this edge is not allowed to move in x direction. uh, so we can it can move in y direction or displace in y direction. Similarly, this edge we need to assign a y symmetry boundary condition. uh, so but yeah, y symmetry means the y displacement of this edge is 0 and we can allow x displacement. So we will be using 4000 Newton. So this is the equivalent pressure. I have just converted into pressure. So we will assign the pressure. Okay. Both are same. So force divided by area. This pressure I will be using for FEA. Another thing to note, we are not going to do a 2D analysis here. Okay, because we want to understand tria or tet element, which is most popularly used in most of the projects. So we will start with the simplest element types, that is tria or tet. Uh, why not tria? Because we cannot model exactly the tria elements in Calculix. Uh, the solver allows 2D elements. So if we model tria element, for example, first order tria element, internally it expands into 3D element. Okay, so this tria will become a wedge element. Okay, so not a tet element. So this is the reason we will not be doing a 2D analysis. So we will take a 3D model and mesh with tet elements and understand the FEA workflow. Okay, so this is the user interface of PrePoMax. You can see there are three tabs here: geometry, FE model, and results. Okay. First thing we need to do is we need to create a new file, and here we need to define the problem dimension, okay, XY or XYZ coordinates. Since we want to do a 3D analysis, I will select 3D. We can select a unit system. So I will select SI unit system, that is turns second. This is the most widely used unit system in most of the industries. So throughout this course, we will consider this unit system. So once we create a new file, the first thing is to do import the geometry. PrePoMax doesn't have geometry or part creation capabilities, so we need to import a geometry. I will import this plate 3D step format. Okay, so this is a 3D plate, okay, with 1 mm thickness, and we can change the name here. Okay, so first thing we need to do is create a mesh. Okay, without that we cannot move to FE model. If I click FE model, I don't see anything here because first thing we need to create mesh. So I will right click mesh setup and say create. There are so many mesh controls here. We will not go into the details of each and every one. As and when required, we will talk about these features. So the first thing is meshing parameters. This is basically to give a global mesh size control. So let's start with this. It pops up this dialog box for selecting geometry. So I will select this geometry. It will turn into red. There are mesh settings. For now, let's stick to basic and default. Once you select the geometry, the uh, the solver or PrePoMax will highlight the maximum and minimum element size. Okay, it will by based on geometry dimensions, part dimensions, it will show a max and minimum element size. So we will go with this default element size, and mesh type we will select first order. Okay, so I will say second order no. So just right click and say create mesh. Okay, so this mesh is not as I expected. I want a uniform mesh or single element in thickness direction. So let me go to geometry here and give more mesh controls. We can select tetrahedral and select this part, okay, and just say okay. With this, we can now create tet mesh, and it is now uniform here in thickness. So we'll not talk about refinement and coarse mesh, all these things for now, because this is the objective of this workshop is to understand the FEA process. So as you can see, once the mesh is done, it automatically moves to the FE model tab. Okay, and now I can see the mesh in FE model. Okay, so there are many things here. We'll not go into each one. Okay, so we will start with the part mesh is ready. Okay, we can create node set or element set, or it is also called group. We can create surfaces for defining contacts. So we don't need this for now. So we can follow this in this model tree. We can follow this process. Okay, one by one. So materials, we need to create material. We can give some name. These are the material models available. Elastic. I will drag it here and define the inputs for elastic material model. 70 gigapascal I will define, that is 70,000 megapascal, and zero point 0.3 Poisson's ratio. So let's go with the linear material. Okay, so material is defined, the geometry or part mesh is done. Now we need to assign this material to the part through thickness. Okay. So right click sections and create a solid section. Okay, since this is a solid part, we'll go with the solid section and assign aluminum material to this section, and region is this part, and we will say okay. Okay, there are no constraints or contacts required here. So I will go to steps. So steps means like what type of analysis we want to carry out here. For example, no, linear static or linear dynamic, non-linear static, heat transfer. So we are going to select a static step, and we will keep geometric non-linearity off for linear analysis, and remaining things we will keep default. Once a step is created, we can rename here also. Uh, this step is created called linear underscore static. Okay, it has uh, field outputs by default no, generated, and we need to define loads and boundary condition for this step. Okay. So let's assign symmetric boundary conditions as discussed. So right click boundary conditions, and we will assign displacement boundary condition to this surface, which is x symmetry. That means u1, u2, u3 are translation degrees of freedom, and ur1, ur2, ur3 are rotational degrees of freedom. Since TET elements don't have rotational degrees of freedom, you can skip this ur1, ur2, ur3. No need to define them. For x symmetric, we will say u1 equal to 0, and u2 is unconstrained. We can name here x symmetric BC. Similarly, we will create boundary condition for y symmetry on this surface, and we will say displacement in y direction is 0. So symmetric boundary conditions are done. The next is loading. So we can assign concentrated or force or uniform pressure. I'm going with pressure because concentrated force, if we have assigned, Okay, it select the nodes. That means the 4000 Newton we have to divide by number of nodes. Okay, because whatever magnitude I define here, it is per node. So to keep it nodes number of nodes independent, let me assign a uniform pressure and this surface. So 4000 Newton is 100 megapascal, and pressure is always compressive, and we want to stretch this plate. So I will say minus 100 megapascal. Okay, it looks all the inputs are done. Okay, so this is the simplest example to get started with PrePoMax and Calculix. So pre-processing is done. The next is this analysis. Okay, so by default analysis one is created. I will edit it and say get C3D4. Okay, so this is Calculix element naming convention. C means continuum 3D 3 dimensional 4 noded element, that is first order tet element. And if you know, this is very similar or same as abacus naming convention. You can go to tools setting, okay, and see the work directory. So I will go to this Calculix. The work directory default is C10. Okay, uh, but use PMX folder as work directory. So yes, okay, that means okay, I will save the model first and give the name cat c3d4. Okay, this will create a prepomax file .pmx, okay, with the name tet c3d4 in our work folder. So here is my pmx file. That means the default work directory is ctemp, but wherever pmx file is there, it will do the analysis in that folder, okay, by ignoring this ctemp. And we can define number of processors here. By default it is one. It is already set 6 for me. So that is done. Now right click this analysis and run. This analysis finished because it's a linear analysis. Okay, we can go to results and it will open a results tab. You can also see or overview the files here in work folder. Okay, so this is a pmx file, that is pre-processing file, and this tet c3d4.frd, it is output file from Calculix solver. Okay, so you can open this file to review the results. So here the file is open, as you can see, tet c3d4.frd, and it will give outputs, displacement, stresses, strains, and reaction forces. So the maximum stress here at the whole location, it is 234 megapascal. So this is a very basic example to explain you the workflow, and we will go into the details of post processing. We will also see the different element types, mesh convergence in upcoming chapters.